others. Okay, my great pleasure to introduce Van Jacobson, who's talking about IGP convergence. Van.
Hello. I didn't actually do much of this project. It was done primarily by Cengiz Alaettinoglu. He's in Australia talking at APNIC, so I got delegated to come here and talk to Nanog. What this is about is our company is doing some interesting stuff that sits on top of IP routing, and in the process of going around and talking to some ISPs about what exactly the problems were and would they be interested, many of them said, but we don't trust IP routing. It looks like it's not stable enough and it's not fast enough, and we're thinking about replacing it with things like MPLS fast reroute. And this gave us some worry. You can't base products on something that people don't trust. So we thought we'd go do some measurements on IP routing, and this is the results of those measurements. This works. Now, the place we're trying to get is seriously sub-second reroute times, down to basically the propagation time, which transcontinental backbone should be around 100 milliseconds. If you can do that, you get better network reliability. Your link failures heal a lot faster. You get good support for multi-service traffic. You can handle things like voice and video with very minor glitches. And you can get a lot of very expensive, very complex layer 2 gear like sonnet rings out of your network because you can trust IP to do the job that right now they're trying to do. But if you look at where IP routing is today, it's like nowhere near millisecond reroute times. Typically, we're seeing convergence times of seconds to tens of seconds. And if you're going to have IP do the job that right now you're doing at layer 2, you need to do a lot better. You've got two choices in this. You can toss IP routing. People who are trying to sell MPLS have made the claim it's inherently impossible for IP routing to converge in sub-second times, and therefore you need something else like MPLS FFR. Or you could figure out what was wrong with IP routing and try to fix it, and at the end, at least you will have figured out what's wrong. Now, it's really hard. It's easy to replace something. It's hard to replace it with something better unless you understand what the problems were in the first thing. So we figure no matter what, you need to go down the second path. If something in IP routing is broken, you need to understand what. Now, if you're doing rerouting for ISIS or OSPF, we're not even going to look at distance vector routing because everybody knows it's junk, but link state routing, like ISIS or OSPF, theory says it should be very good, that since everybody has got a copy of the topology, their own local copy, and it's the same everywhere, it's very hard to tell lies, and the rerouting should happen basically as fast as everybody gets the link state packets, and it should be loop free. In order to do the rerouting, you've got to detect that there was a failure, find out that something went wrong. You've got to tell your friends that you detected a failure, so you're going to flood a link state packet, and then you're going to compute your new distribution trees based on the new link state after that failure. So we did experiments to measure each of these times, since they're completely independent, on Cisco 7200s, the highest end 7200, and I forget the model number. And it was running both 12.0S and the most recent version of 12.1p, and Juniper M40s that were running 4.1. So all of the, we believe the high-end routing engines, 7200s, are, I think, the same routing engine that's used in GSRs and other Cisco platforms. So what we measure here for routing performance should map across the product line. And I think the M40 is Juniper's top-end routing engine, but I'm not sure. Okay, so detection there's two ways you can find out about a failure. The link level can tell you, or the protocol can be talking to its peers, and if that communication stops for a while, it can say, oh my God, I've lost a peer, or I've lost a link. The ISIS spec allows both of these. The link level detection should be the fastest, at least in theory. There's some places where it won't work at all, like if you've got two hosts connected to an Ethernet switch, you disconnect one of the hosts, the switch knows it's gone, but its peer doesn't know it's gone. Nothing upstream of the wire where it connects to the switch gets the failure indication propagated. So you've got to have something like a hello mechanism. And it turned out, since the vendors know you've got to have hellos, it looks like the link level detection is implemented sort of spottily. We saw on several links where it didn't happen at all. We could unplug the link and nothing happened in ISIS until the hellos timed out. Or we'd unplug the link, the carrier light would go out, and then 15 seconds later, the process would get told, oh, by the way, this link just went down. So, now, given that spottiness, it looks, and the scenarios where link level detection doesn't work, your main source of detection is going to be hellos. How well can you do on hellos? Well, the ISIS spec says that routers should send a packet to each other by default every 5 to 10 seconds, and at most every second. And when you lose 3 of those packets, you should declare that your neighbor is gone. So that sets a bound on, you can't find out that there's a problem in your network for at least 3 seconds, because the minimum you can set the time is a second, and you've got to lose 3 of these packets before you know something's gone. So we did a test on the details of detection, which is hook up 3 routers in a triangle. The picture that's on the left, we biased the metrics so that we could send pings from a workstation. They go clockwise round the circle, and then we turn the power off on that router that's in the upper left-hand corner, the one that's yellow in the second picture. And the picture at the bottom is the packet trace that we got from the workstation watching traffic between these 3 routers. So at the beginning, you see the ping, the echo replies coming back. They're coming back once a second. Time 0 on this trace is where we unplugged the router. That blue packet a few seconds before time 0 is the hello that happened. It's happening on some random clock. It happened a little bit before we unplugged the router. The dotted lines that you see in the middle are where hellos would have been had the router still been alive. So as soon as we unplug it, the pings stop. There's no hellos. That line is sitting right about 26 seconds, and I'm unfortunately colorblind and don't know its colors, red or green probably, is the link state update packet when router 2 has timed out the 3rd hello. The LSP appears right where the 3rd hello packet would have been, so it's 3 times 5 seconds, the default timeout on this particular router. So it sends an LSP saying, oh, by the way, this link is gone. Its peer also sends an LSP. They're trying to figure out who should own the virtual node for the network. And then there's a little bit of a delay. They finally do the SPF calculation, and then the pings start coming back again. So the total time there was about 33 seconds from when we cut the power to when we got the reroute. And there were no surprises. Happened exactly according to spec. Say, well, if the spec didn't say 1 second is the minimum hello time, and we could crank it down to whatever we wanted, crank it down to microseconds, what would be the real physical constraints on the hello packets? How fast could you send them? Clearly, you can't send them any faster than the link bandwidth allows you to. If you fill the link with hellos, then lots are going to get discarded, and you'll lose your adjacency. But there's a question about if there's other traffic on the link, at what load do you start losing a significant number of hellos? And we did, Haobo, the other author on this paper, did a set of simulations looking at that with drop tail gateways and priority queuing of the hellos and red gateways, pretty much all the parameters we could think of for doing queuing on the hellos. And the answer was, you don't get into any trouble until you fill the link with hellos. The other traffic doesn't matter. All that matters is the intensity of the hellos, and by the time you get to the point where you're filling the link with them, then you start to lose a lot of them. And that's what this 3D curve says. One axis of it is the total load on the link. One axis is how much of that total load is hellos, and the vertical scale is how many of those hellos you're dropping. And it turns up just when you fill the link with hellos, and it doesn't really matter what the other traffic is doing. That says that you can run the detection pretty much as fast as the bandwidth of the link allows you to run the detection. You'll get, if you keep the hello bandwidth to a negligible fraction of the data traffic, like hellos are 1% of the data traffic, so you're not taking your revenue away with this routing crud, then you're not going to lose any significant number of the hellos. And so you should just detect real errors and not false packet drops. Okay. So, in terms of designing the protocol, the ultimate limit on the hellos is just the link bandwidth. And the only thing that's stopping us from doing fast detection right now is the protocol spec has a limit in it of 1 second. If we change that limit in the spec, then we should be able to do detection as fast as physical law allows us to do detection. That doesn't mean that you can set the detection time down to, say, a microsecond in an OC192 link. There's physical laws that limit the detection. They have to do with the noise on the link and the delays imposed by various processes as you're going through your router. The issue in the protocol design is to make sure that you're constrained only by those physical laws and not by some number that somebody pulled out of a hat saying, oh, hello should only happen 1 second. So you still have to do engineering to pick the right time, and the time's a few tens of milliseconds, generally set by the noise spectrum. But that time should be a property of your network, not a property of the protocol. Great. There's another issue if you're doing fast detection in you can track transients. If the telco has decided to yo-yo your link, if your Sonnet Mux is having a little trouble getting its phase lock and so it's coming and going at half-a-second intervals, you don't want to be generating LSPs, routing changes, through your network at a very high rate. Now, the usual way of dealing with this, for example, the way it's dealt with in OSPF, is you make the detection of bad news be very fast, so you're aggressive in saying a link has gone away. You make the detection of good news be very slow. If you've got a working path because you rerouted around some failure, you're reluctant to change from that working path back to a better path unless the better path has been there for a little while. And so the current spec for ISIS says that good news and bad news should be treated exactly the same. Detecting a link coming up, you treat with the same, filtering the same 3-second wait or 3 hello wait that you do with a link going down. Should be relatively trivial to change that part of the spec so that you treat down much faster than up. When you do that, you can dial the stability, in much the way that we can dial the stability of OSPF in spite of having fast detection of failures. Okay, next step in routing is propagation. You found out that something has gone south. The guy who originally detects the failure turns that into a link state packet. He floods it to his adjacent neighbors, and then they take that packet absolutely unmodified. They're not allowed to touch it. And they flood it to their neighbors on and on until it's gone through the entire network. Since nobody but the guy who originated that packet is allowed to do anything to it, the flooding should go at speed of light plus store and forward delays. So it's 1 packet time per hop, so it's a packet time times the diameter of your network. So it should be fraction of a millisecond. So we set up a test to measure this one. It consisted of a workstation with 4 Ethernet interfaces, and we hooked up 3 routers, basically with 3 point-to-point Ethernets between them. And the workstation could look at all 4 of the Ethernets involved in this experiment, and on the port labeled 0 there, it could inject LSPs. So it could inject an ISIS link state change, which we can then watch propagate through those 3 routers. Now, back on this picture, remember back at the gap between time 26 and time 33, the LSP has gone out at time 26, but the rerouting calculation doesn't happen until time 33. And we said this is going to limit our convergence to, we can detect things happening to at most 5 seconds because there's this artificial delay. It's a delay that's put in there to account for the cost of the SPF calculation, which is a significant load on the CPU, which I'll talk about next. But we wanted to set that delay to 0 to see what was the best we could do on propagation of the failure. So we set the delay to 0. Okay. This picture, the bottom axis is the hop. The y-axis is the time at which we see the LSP go through. So we inject it at router 0 at time 0. It pops out about 300 milliseconds later at router 1, and then about 300 milliseconds after that at router 2, so on. And the time scaled according to the size of the topology. We injected topologies of 500, 800, and 1,000 nodes, and the amount of time per hop was linear in the size of the topology. So what this had said was this SPF calculation, computing a new tree, is a major hit on the CPU. People, the router vendors know this. They don't want to do it any more times than they have to. When you get a link state change, there's usually a bunch of link state changes that are close to it. So in order to only do the calculation once and get good convergence, they delay the initial calculation until you've collected several LSPs. But that can delay the propagation of your LSPs. If you change that time to 0, say, these are really fast boxes, I'm going to let them compute the new topology as soon as they can, and I want them to flood as fast as they can. Well, the spec doesn't call out the timing between the propagation and the SPF calculation. And if you implement the router as, say, single, non-preemptible process that pulls off an event and does something, when it's back, it pulls off another event and does something, it can get the LSP, do the SPF calculation. Only after the SPF calculation can it go back and say, now I need to flood the LSP. But what you want to do in link state routing is flood as soon as possible. Your network is this massive distributed computer, and what you would like to do would be to get it all computing at the same time. That's going to give you the quickest convergence if you can get everybody working at the same time, as opposed to I work and then I tell the next guy upstream to work and then he tells the next guy upstream to work. If you do that second, then you get this convergence picture, and by the time you've gone 3 hops, you've waited a second for your routing to converge, just because you're waiting for everybody to do their calculation. And you can end up with significant topologies of being the diameter times whatever time it takes to do the SPF. Issue here is the spec needs to call out explicitly what you do when and what the priorities are. And it's basically do the hellos, because if you don't do the hellos, you lose your adjacencies, and then your network gets unstable and dies. Do the SPF flooding, or do the LSP flooding, because if you don't do that, the other guys won't hear about the problems until you're done with your computing. And finally, when you've got time left over, do your computing. spec doesn't call out those priorities, and so you can get some weird pictures and some long delays. Okay, lastly, the previous experiment, the propagation experiment, showed that the shortest path computation was huge. It was hundreds of milliseconds going up to seconds. So Cengiz developed some software that would let us check topologies of arbitrary size, inject them into a real network with real routers, and look at how the SPF scaled as a function of various parameters of the topology, nodes, edges, and the like. So we hooked up all of the router boxes that we could find into a real topology. We hooked a workstation up to them running his IS-Talk software, generated synthetic realistic topologies using the Georgia Tech topology generator, generated them on that workstation, and then injected them from that workstation into the router farm, and then measured what the SPF calculation cost on the various routers. So this is injecting random topologies of average degree 5, which is consistent with the measurements that we've got of physical backbones. The bottom blue line there was we wanted to have an idea of what was reasonable to expect from these routers. So Haobo coded up the best Dijkstra, heap Dijkstra algorithm that he could and ran it on his laptop using the same topologies that we were injecting into these routers. The blue line is Haobo's heap Dijkstra running on his laptop. The next 3 lines are measurements of the various routers. It's sort of uninteresting which router and which OS. What's interesting is there's a huge variation in times. That by the time you get up to 1,000 node topologies, the vendor implementations can take between 10 milliseconds and half a second in order to do a single tree calculation, single SPF calculation on the topology. Now, this may look like Haobo is doing some wonderful code and you just need to move it to routers and we solve all the problems. That vanishes if you put this on a log scale. Pretty much everybody's got the same shape except, let's see, we fit curves to all this data. The top one there is n squared, which is if you implement Dijkstra in the naive way, it iterates over all the nodes, and in each iteration it iterates over all the other nodes looking for the lowest cost one. And so it's basically an n squared algorithm. If you implement it sort of the smart way, you iterate over all the nodes, but you do the search by a heap, so it's an n log n algorithm. So the 2 lower vendor curves are clearly heap Dijkstra. They fit an n log n curve. The upper curve is an n squared curve. You can see that on this picture, that the shape of the upper one, if you look at the bottom of it, it's seriously different than the other 3. We didn't, one vendor's guy, we didn't measure all the way down. And Haobo's, which was an n log n implementation, had the same shape of everybody else. Problem with these guys is they're all going up. They're all fairly steep. And it doesn't take much to get to a topology where even good tuning is going to kill you. And in terms of the doesn't take much, for reasons that aren't entirely clear, most ISPs don't run or at least most of the tier 1s that we found don't run the protocol on the real topology. They construct a virtual full mesh topology using ATM or some other pathology, and then they run routing over that full mesh. Well, the full mesh bumps the number of edges up to n squared, right, since every node has to talk to every other node, and routing is sensitive to that. So this is looking at the time scaling for full meshes running up to about degree 300 nodes. Heap Dijkstra tends to do badly on full mesh topologies, so the second line there is actually the n squared algorithm, the top line is the n log n algorithm, and then one of the other vendor implementations, and down the bottom in blue is Haobo's algorithm for reference again. On these, Now, 300 is smaller than the smallest tier 1 that we know about. The smallest tier 1 that we've talked to is a mesh of 400 nodes or 16,000 tunnels. But 300, you're already to a second of CPU time for every routing calculation. So every time you get a state change, you've got to do this calculation. You blow 100% of your CPU for a second at every hop. That means you're going to take a hell of a long time to converge, at least a second because of this calculation. And it means that your network is a lot more brittle because your routers have gone away. If you're getting changes in your topology once a second, if link state changes, then you've got no router CPU cycles left, so they can't do SNMP or anything else useful. Fixing it is probably not a matter of code tuning. Okay, so at the top we've got the 4 graphs that I saw in the previous picture. At the bottom is a different way of doing the SPF calculation. The Dijkstra calculation was originated in 1964. It's a wonderful algorithm, but in 40 years we've actually come up with some improvements to it. And Haobo implemented one of those published improvements. It's an incremental Dijkstra algorithm. Its scaling, rather than being n log n, is log n. And it really does scale like that. As your network gets bigger, it gets faster. As you're more connected, it can find an alternate path in one hop for the most part. And so its convergence gets a lot faster. If you move to this style algorithm, then the calculation time immediately goes from seconds down to microseconds, and it stays at microseconds. And that's true independent of the size of the network. Log n grows very, very slowly. So almost to the summary, a final note. One thing we were looking for was some support for the rumors that we heard about routing as unstable. We were just beating the hell out of these routers. We were injecting topologies with 50,000 nodes and edges. All the routers were running 100% CPU saturation. We were giving them LSPs at 100 times the rate that they could process them. And then we were just randomly unplugging links and powering off routers. We never saw anything that looked like instability. I mean, everything just ran rock solid. Slow as molasses. All the routers were saturated, but absolutely solid. The topologies were always reasonable. Things never bounced around. And when we started looking for why is it so good, we found various things that the vendors were doing, like generating hellos at very high priority so that you don't lose adjacencies when you're loading up the routers. A lot of little clever things that made it absolutely rock solid. We talked to Dave Katz about some of this. He said, well, yeah, you know, people have spent the last decade beating on my software with baseball bats, and, you know, it gets a little bit tough after that. And, you know, this stuff, the routing software has really profited from the decade worth of very large-scale experience in the internet. Generally, the bugs that have been found and the meltdowns that have happened, the vendors have put in fixes for them. So, given that we've got some pretty good stuff, and we've got some measurements that say the real problem here is basically granularity of timers and the cost of doing this vintage 1964 algorithm, it's actually not a very big deal to evolve the stuff that we've got, which works pretty good, to something that works pretty good in sub-second times. And we didn't see anything that said that we couldn't do IP routing at the theoretical minimum time for doing rerouting, which is the propagation time. There are some things you need to do to get there, which is switch to a modern algorithm. It's the biggest thing, but it's a small thing. It's replace a little tiny piece of code inside the routing implementation. Change the granularity of the timer, the hello timer, and change the spec so it allows different detections for up and down events. None of these are completely trivial, but all of them are pretty small pieces. And at that point, you've got IP routing, regular, vanilla, robust IP routing, that does rerouting as fast as any physical system can do it. That's the end. Except I'd like to acknowledge we got a lot of help from the Global Crossing Production Testing Lab in doing some of the initial measurements, and both Cisco and Juniper helped out with equipment on doing the testing. And a thing that we haven't been able to do but would very much like to do is measure routing inside of real ISPs. This is interesting. Routing takes a long time to converge, but if you get one route flap a week, who gives a damn? It's not worth fixing. We don't know. We've talked to people who say, well, I don't think it's very bad, but they don't know how bad it is. So if you're interested in working with us and doing some testing, if you could contact Cengiz at Packet Design, we'd be grateful. That's it. Any questions?